Now we have two types of superconductors that we should mention. The type 1 superconductors, they have a single critical field. They're characterized by a single critical field. Examples include aluminum, lead. These are elemental BCS superconductors. They fall into this type 1 category. And they tend to have a low critical field, low HC value. So it's not a very good material to work with in that sense because the critical field is low. So the maximum current that they can maintain is going to be low as well. And for type 2 superconductors, we have two critical temperatures and two critical fields at a constant temperature. So two critical temperatures, TC1 and TC2, and also two critical fields, HC1 and HC2, at a temperature, at a constant temperature. So you can see the magnetization versus field plot for type 1 and type 2 superconductor. The dotted line is the type 1 superconductor. So you can see there exists a single critical field. Now for a type 2 superconductor, we have two critical fields, one HC1, the other one is HC2, and we can divide this into regions. So below HC1 we have a fully superconducting state. So this is the superconducting state. Between HC1 and HC2 we have a vortex state, which is a mixed superconductor and superconducting and normal state. And above HC2 we have the normal metal state. Okay, so that's for the type 2 superconductor. For type 1 superconductor, on the other hand, here we have the superconducting state, and here we have the normal metal state above the critical field. Okay, so so let me clarify that this is for type 2, this is for type 2, and this is for type 1. So in a type 2 superconductor, when we have T less than TC1, all the flux lines are completely expelled. Chi is equal to -1. So between TC1 and TC2, on the other hand, we have a mixed state, or also known as a vortex state. So what happens in this case is that the flux lines can run through narrow regions of non-superconducting material surrounded by vortices of supercurrents protecting the rest of the superconductor. So if this is your type 2 superconductor for temperature between TC1 and TC2, what we see is that there are normal metal regions like this. So we have normal metal regions. And then we have electrical currents that can pass, since we said it has to be a surface current here, so electrical currents can pass through these and forming vortices, and also because these are normal metals, the flux lines can go through the normal metal parts, but the rest of it is in the superconducting state. So here we have the superconducting state. Okay, so flux lines run through narrow regions of non-superconducting material surrounded by vortices of supercurrents. So these blue ones are supercurrents. Supercurrents form vortices because when a flux line passes through it, there is an induced current, and that is going to be forming a vortex around these normal metal regions when we have a magnetic field turned on. Okay, so H less than Hc2. Okay, so examples of these superconductors, basically all high Tc superconductors are type 2. So they're all type 2 superconductors. Okay, and as for the theory of superconductivity, there is the theory developed by Bardeen, Cooper, and Schrieffer in 1957. BCS theory was developed. Basically, we consider an electron moving through a conductor. This electron will normally attract the nearby positively charged ions in the lattice, and the deformed lattice causes another electron with opposite spin to move in and correlate with the previous electron so that they form Cooper pairs. So this is based on the idea of forming a Cooper pair. So Cooper pairs, these are electron upspin, let's say, deforms the lattice, an electron with downspin is attracted by the deformed lattice. So in a Cooper pair we have electrons with opposite spins. If the temperature is low enough, then the phonon modes are frozen, so the atomic vibrations are minimized, so that this electron lattice interaction is possible. So for T less than Tc, phonon modes, lattice vibration modes, that is phonon modes, are frozen, and we see that direct electron lattice interaction is possible. Okay, so with the help of the deformed lattice, the Cooper pairs flow without friction through the superconductor. So Cooper pairs flow without friction, enabled by the deformed lattice. So that is the main idea. And another important feature of superconductors is that I have to put a remark here. Since there will be an energy cost for breaking a Cooper pair, there is a critical energy that has to be supplied for breaking the Cooper pair. So superconductors have an energy gap. And basically that is the amount of energy we have to supply, delta E needed to break Cooper pairs, and this can be basically found out experimentally that only certain frequency photons are absorbed by the superconductor. So that corresponds to this energy gap basically. As far as the applications of superconductors go, we can talk about one important application, that is superconducting quantum interference device, SQUID. This utilizes the Josephson effect, and it's based on the idea that when you have a tunnel junction between two superconductors, this is a tunnel barrier, the tunneling supercurrent the critical super electron tunneling current is a very sensitive function of magnetic field. So using these Josephson junctions, one can measure magnetic fields so fields down to 10 to minus 18 Tesla can be detected. So it's a very, very sensitive technique. And on the other hand, since we can have very large magnetic fields created by these superconductors, so superconducting magnets such as niobium tin are used, for example, in the Large Hadron Collider in CERN. So I'm going to give a link to a simple explanation with an animation of the Bardeen-Cooper-Schrieffer theory, and also a discussion of the superconducting magnets in CERN as well. So these are also useful in accelerator applications. Okay, so we talked about types of superconductors. Type 1 superconductors have single HC and single TC. Aluminum, lead, elemental BCS superconductors, they tend to have a low HC, so they're not very useful. The most useful superconductors are type 2, which have 2 TCs and 2 critical fields. This perfect diamagnet state is pure superconducting state, is for temperatures below TC1 and field below HC1. When we have the temperature in between TC1 and TC2 and the field is less than HC2, we're going to have a mixed state, which is called a vortex state, because we have regions of normal metal inside the material. When we apply a magnetic field, the flux lines can pass through these normal metal regions, and they induce currents flowing around them, forming supercurrent vortices. So They are in a vortex state. All high TC superconductors are type 2. And the BCS theory tells us that below a certain critical temperature where the phonon modes are frozen, the electron lattice interaction becomes important. An electron passing through the lattice deforms the lattice, and the deformation attracts a following electron with opposite spin, and we form these Cooper pairs that can flow without friction through the deformed lattice. Because it requires some energy to break these pairs, superconductors have an energy gap which is witnessed experimentally by looking at the absorption spectrum. We find that only certain frequency photons are absorbed. Important applications include superconducting quantum interference device, ultrasensitive field detectors that uses the Josephson junction technology, the supercurrent, supertunneling current in a Josephson junction is a highly sensitive measure of magnetic field, and also superconducting magnets that can apply fields up to well easily about 10 Tesla are in use. For example, in CERN they can be used in accelerator applications.